In this video, I'm going to discuss one of the question from ISRO 2018 EC. So let's start. For a circuit given in figure, switch K is close to position 1 at time t equal to 0, and after one time constant, this switch K is moved to position 2, and we need to find the current before one time constant, that means at t equals to Tc minus just before that one time constant and just after that one time constant respectively, and the value of e to the power minus 1 is given. So first thing what we need to understand before solving this question is, if at t equal to 0 the switch is getting closed, it is given that switch is getting closed at t equal to 0. First, the most important thing is, before t equal to 0, what will be the condition of this circuit before t equal to 0? So the circuit will initially from t equal to infinity to t equal to 0. That means if the switch is getting closed at t equal to 0, so before t equal to from t equal to infinity to till t equal to 0 minus, if I'm taking this as 0 minus, at very close to t equal to 0, but just for the sake of showing it on paper I have taken it here. So from t equal to minus infinity to up to t equal to 0 minus, the circuit will be in steady state. Now as at t equal to 0 the switch is closed, the transient will begin, and transient state will continue till t equal to 5 times of tau, where tau is nothing but the time constant of the circuit. So this is a state from t equal to 0 till t equal to 5 tau. In networks we consider t equals to 5 tau. Up to t equal to 5 tau is transient, whereas in other subjects like controls we consider t equals to 4 tau as the time for transient. So till from t equal to 0 to t equal to 5 tau, this will correspond to transient state, and this is our area of interest basically, mostly in networks during transient analysis and all. And from t equal to 5 tau up to t equal to infinity, this is the circuit is back again in steady state. And why we have the transient state? It is only because of energy storing elements like capacitor or inductor. Since the capacitor store energy in the form of voltage, therefore for capacitor all the analysis is done in terms of voltage, and in inductor the energy is stored in terms of current, so we do all the respective analysis in inductor in terms of its current. So let's focus on the question. So in this question it is said at t equal to 0, at t equal to 0 the circuit is getting closed. Before t equal to 0 the capacitor was the circuit was not closed, so capacitor was not energized. That means that capacitor was unenergized. It was as good as uncharged capacitor. That means charge in the capacitor is 0. That means since nothing is given, that any condition is not specified. So when at t equal to 0 the switch is closed, in one time constant, constant, how much charge will get accumulated in the capacitor, that is given by that means how much will this capacitor will charge. Actually from charging curve we know that in one time constant, this is the charging curve. If this how much the capacitor can charge, the maximum value it can charge up to which it can charge, that means in steady state will be 20 volt. So in one time constant in tau it can charge up to whatever is the maximum value we see. If suppose this I'm considering as V, suppose if that I'm considering this as V, so Vc will be equal to V times 1 minus e to the power minus 1, right? It can charge up to this. And how I got this I can actually tell you from equation. I'll do that. For the first order equation, which is given at V of 0 plus, sorry, V of infinity plus V of 0 minus V of infinity e to the power minus t by tau. Okay, in charging equation. Initial charge was 0, V of 0 will be 0 because nothing is given. And at infinity what will be the equivalent circuit at infinity? We can draw like this. The capacitor will be open circuited. Why? Because the capacitor has stored the sufficient energy, and now the current through the capacitor is 0, and since the current is 0, if a current is 0 across any terminal, we say that it is open circuited. That's why this will be open circuited. And if it is open circuited, the voltage across this is going to be 20 volt. I'm talking about, I'm only considering this case. I'm not considering when the switch is moved from position 1 to position 2. So till now we are discussing this only, that how we got this. V is equal to V1 minus e to the power minus 1. So if V is 0, what will be V infinity? At infinity, this complete voltage V is going to appear across this open circuit terminal. So that is going to be 20 volts. So V infinity will be 20, or whatever is the value of maximum value. We can say V infinity is nothing but in this case will be V maximum. So directly we can say V of t is actually equal to V maximum, or which is 20 times 0. This is plus, and minus V infinity is what? V of maximum e to the power minus t by tau. So which is nothing but V of t is actually equal to 20 1 minus e to the power minus t by tau. This is tau, and we know what we have to find: the current at just this time instant, at one time instant, just before one time instant. So let's first find out the voltage. That means up in one time instant, how much the capacitor is charging. We directly also we know that it will be 20 into 1. Since it is one time constant, so t is actually equal to tau. So it will be 1 minus e to the power minus 1. So this is how we got this formula: V is equal to V 1 minus. This is basically the charging of capacitor. This equation corresponds to the charging of capacitor. This is a standard equation, and this is how it is derived. So V of t will be this, which is nothing but 20, and they have already mentioned the value of e to the power minus 1 is 0.37. Well, these are standard values, you should remember. So 1 minus e to the power minus 1 will be 0.632, and if you'll multiply this, you will get 12 the value corresponds to 12.642. okay, now we need to find the current at t equal to 0 minus. So at t equals to tau minus, the value will be, the current I is given by this voltage V. You can see this voltage V minus whatever the voltage it is storing. This is tau minus upon whatever is the resistance. So this will be 20 minus 12.46 upon 500, which is equal to 0.0148 amps. Okay, now we know that at t equal to tau plus, what is happening at t equal to tau? This switch from terminal 1 is getting, we are removing it from here, and we are connecting over here. So when we are connecting, the corresponding circuit will reduce to, initially here it was 20 volt, now it will be 40 volt. And we know that voltage across a capacitor is a continuous function. If voltage across a capacitor is a continuous function, that means voltage across capacitor at tau will be equal to voltage across capacitor at tau minus will be equal to voltage across capacitor at tau, which is also equal to voltage across capacitor at tau plus. So all these voltages will be nothing but the same value, because voltage across capacitor is a continuous function. So this, we can replace this with a voltage source. The capacitor itself we can replace, because this is a transient state. We are here, the analysis was starting from t equal to 0, but here since the switch is, we are turning the switch in different mode at t equal to t naught. So our analysis will start from t equal to t naught, not from t equal to 0. So this capacitor, we are actually replacing this capacitor with a voltage source, because the capacitor is energized, it has charged up to 12.642 volt. So this capacitor I can replace with the voltage source of 12.642. and what we need to find, we need to find this current I. So what will be the current I can say the current I will be this voltage source 40 minus, since the capacitor is also acting as a charged element, that is voltage source, so 40 minus 12.642. and what is the resistance, what is the value of the resistance? Resistance is 500 ohms. So this divided by this value divided by 500, so this will correspond to approximately 0.054 ampere. So this is the current I at tau plus, and this is a current I at tau minus. We should make sure we should know one thing, that the voltage across the capacitor is a continuous function but not the current. This is very important point. Similarly, the current across the inductor is a continuous function but not the voltage. So this is one thing which you need to keep in mind. Let's check the option. With the option, if you are going, option A is the correct answer for this. I hope this is clear. Thank you.